So when you hear the word extrema, don't let it freak you out. Like, I know it's the first day back, but what we're talking about here are like extremes, like highs and lows. So if we're looking at a graph, when we say extrema, we're talking about minimums and maximums on a graph. So for example, if I was just to quickly sketch one, right, these would be the minimum points that would be interesting to me, and then these would be the maximum points that would be interesting to me, called the extrema. Now, one thing you might notice is you might be saying, well, Mr. Joyce, what if it looked like this? You might think that's interesting as a minimum, and you might think, well, shouldn't we consider this too? But basically, we're going to go through the strategies of finding these points that give us the highest and lowest values, because this might be like a graph of, efficiencies or, profit versus loss, something like that, where we're trying to find either the most or the least involved. So rather than just guess a bunch of times, we can use some of our calculus tools to give us some exact values. So let's just take a look here then. This graph, x cubed minus 3x squared, we'll start by throwing it in the graphing calculator. So x cubed minus 3x squared.
That's just x cubed.
Thank you. Okay, so there, and I'm going to line up my window to match the one I've already chosen here. So that'll be a window that goes from, like, I guess, -4 to +4, and probably -6 to +6. Okay. So there's a rough sketch, and I'll transfer it onto our page here. So let's see here. It's going to look sort of like, I don't know why it disappeared here, but I'll put the x-axis back on the graph. And a quick sketch would look something like, something like that. Now, as I mentioned, what we're going to be interested in working out today are how we find these points here. So how do you think you could use calculus to do it? There's something very unique about those points. Yeah, you might think about it like a vertex, but something specifically that calculus can help a lot with finding these points.
Oh, it's tangent.
Yeah, there's horizontal is where it's definitely not an asymptote though, but something horizontal we're looking for. Tangents, yeah, it's a horizontal tangent. So if you look at both of these points, there's a horizontal tangent at them. And that should make sense to you because if you are the largest value, that means you increase all the way up to you, and then you can't increase any more or you wouldn't be the largest value. So you have to stop increasing or you're not the biggest. Same thing with the smallest. You have to go down, 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 and at some point you have to stop decreasing or you're not the smallest. So we have to find a value where they're equal to 0. So if we call these critical points, and these are where the derivative is equal to 0. And this is kind of a strange one. Not everyone picks up on this. But it's not just where it's equal to 0. We also need to think about where it might be undefined. Can anybody think of why it's important that we also consider where it's undefined? Yeah, maybe an asymptote might have something to do with what we're looking for, but these critical points that we're looking for, the undefined is, maybe I shouldn't be so tough on you your first day back, but I'm going to give you an example of a graph where it's undefined. Maybe you can tell me at least what the graph is. Recognize that graph? Yeah, it's roughly the absolute value graph, right? Do you see somewhere there the derivative's not defined? Right, and that would be a point of interest to us, that vertex kind of looking piece at the bottom. What does it do at the bottom there? What do we call that in calculus, that bottom piece? The bottom piece. Do you remember what we call that? Like, it might not be the absolute value graph. Maybe it's a piecewise graph that goes like this. What did we call that when we were talking about derivatives? It doesn't exist there. The derivative, you can't put a tangent there. But do you remember what we called that? Well, the limits won't exist when you look for the derivative. That's why the derivative doesn't exist. You get one from the left and one from the right. Remember, it looks like this, though. It starts with a C. Yeah, a cusp or a corner, right? Those are the things we're looking for, because when we run into them, they might represent a minimum or maximum as well. It might not be, like this one is not a minimum or maximum. However, it might be a corner that looks something like, maybe it does this where it goes down and spikes up. This would be a minimum value here. And we wouldn't be able to detect that unless we also looked for where it's not defined. Okay? So in the original graph, the critical numbers, they happen here at x equals 0 and x equals 2. And if I wanted to double check that, the derivative is 3x squared minus 6x. So if I factored it, then I could see it's going to be equal to 0 once here where x equals 0, and another one when x equals 2. So at both spots, the value of the derivative, or the slope of the tangent, is going to be 0. So there's a handy little theorem in your textbook. It is a mathematical fact. It is not something that you need to worry about. It's been proven that if you have a set of critical numbers, your minimums and maximums must be inside those critical numbers. So let's write that down. Let's call it the set of all critical numbers. Okay, so here's the first important thing that you have to realize. Critical numbers aren't magic. They just help eliminate all our choices. If I was just to give you a function before right now and ask you where do you think the relative minimums and maximums were, unless you come up with a strategy, you have an infinite number of places where you're going to guess, because you don't really know unless you start checking. But now that you have a strategy, all that's done is reduce the choices for you. Critical numbers, because something is a critical number, does not necessarily mean it's going to be the thing you're looking for, like a minimum or a maximum. It just limits your choices down. Like, for example, in this picture, there's 2 of them, but you might only be looking for this one. You might also find that there's a critical number that's neither a minimum nor a maximum. It might look something like this. Here's a graph where the tangent equals 0. Let's just say it's flat when it goes through there. But it's not a minimum or a maximum. So being a critical number does not make you an extrema. But if you are an extrema, you have to be in that group of critical numbers. So the only reason I'm cautioning you about this is you actually have to then take those critical numbers and go looking for the maximums or minimums with it. Okay. I also use this word here, relative and local. What that means is any relative extrema means that you are a maximum for some part of the graph, or a minimum for some part of the graph. If you look at our first example here, here is a maximum, and I would say it's maximum, we could probably stop. We'd have to chop the graph right there. So this point is the maximum as long as I'm somewhere to the left of that green line, right? It's not the maximum if I go, that point right there is larger than the one that I found. Okay? So this is a local maximum or a relative maximum, meaning it's only for a very small part of the graph. Same thing with this minimum. This minimum is for a piece of the graph. It may not be for the whole thing. Okay, so find the relative extrema for this graph on that interval from -1 to 2. So let me walk you through the process. This is our first most important thing we're doing. We're looking for critical numbers, and critical numbers are where the derivative is 0 or undefined. So let's go to it then. If we find a derivative, we'll have 12x cubed minus 12x squared. So I'll take out what I can with some factoring. And this is a polynomial. It is well behaved, meaning there's nowhere it's undefined. So I have no problems other than where it could be equal to 0. So my critical numbers would be x equals 0 and x equals 1. That's the only spot where there could be the minimums and maximums I'm looking for. It just so happens that they fall into the range I'm looking for. Right? So let's figure out what they could be by testing them. Here's how you test them. If I put in f of 0, what value do I get?
0.
Good. And if I put in f of 1, what would I get? -1. Remember, we're using the derivative to tell us information about the function. So this here is the function, not the derivative. I found out the points where there's going to be extrema on the function. Now I'm actually seeing, what are they? 0 is bigger than -1, so what do you think is happening to the graph there? Well, yeah, you'd think that you'd be inclined to say that this is a maximum and this is a minimum. Okay, let's take a look at the picture and make sure that everything is the way we expect it. So I'm going to change this graph to be 4x cubed minus, do I have the right graph here? Sorry, no I don't. 3x to the 4 minus 4x cubed. So 3x to the 4 minus 4x cubed. And I only need to see it from -1 to 2. So I'll just shrink this down, take a look at it. Okay, so there's the picture we're looking for. Now, there's that value at 0. Again, notice that it does have a tangent that's 0. But would we consider this a relative minimum or a relative maximum?
Yes.
Is this a relative minimum or maximum?
No.
It is not. If you're still wrapping your head around what it means for some place that this is the smallest or largest value. That's not true, because if I was to say, let's say just make my chunk of the graph from here to there, it is neither the minimum or the maximum. There are values which are higher and lower than it at the same time. Like right where the mouse is, it would be higher than the value at 0. Where the mouse is here, it would be lower. So as I zoom in, there's no interval where it is the largest or smallest value, so it's not extreme. It's not the extreme value I'm looking for. So this one we would say, nope, it's not what I'm looking for, not extrema. This one, however, is extrema, because I can see that where the mouse is pointing is the lowest possible value if I'm close enough to it, right? So that is a relative minimum. That's what we would call that. And there's also something else I have to check about on this graph. I'm going to actually expand this a little bit more because it doesn't quite show it, so I'll just expand my window a bit. Hopefully this does it. Yeah. So if you're trying to zoom in on what the biggest and smallest values are on this graph, we've forgotten to do something here. What's the biggest value? on this picture, right, because we're only looking from -1 to 2. This might be like, maybe you're looking at a factory and they're giving you some data about your workers. You can't have them working beyond, 24 hours a day. There's certain limits within what you're doing. So your window is going to have some limits too, like this one. So what's the biggest value within this window? Well, it could be 15. I don't know exactly what it is, but it happens at x equals 3, the end point. So right here, this is the largest value I can see. So that's the one that's actually going to be biggest. So what my point is if you think about that picture, it's something like this. And here was our relative points. These endpoints are also important to me because the endpoints could tell me which one's biggest and smallest. So out of everything I did, all I have to do to find the biggest and smallest value is check my critical points and check my endpoints. If it's not within that group, it's not the minimum or maximum. So all that I have to add here is what's the function at its endpoints. And I'll just jog your memory here. Since you're going to be using your graphing calculator in some of this stuff, it's helpful to use your table. So I'll just show you, you go to the table setup, which is second function window, and you want to make sure that the independent variable is set to ask. That way you can plug in the values. And then I just go to the table, and I could plug in the value at 0, the value at -1, the value at 1, and the value at 2. That way you don't have to do it by hand. So that's over here, 0 is 0, -1 is 7, 1 is -1, which we already wrote, and 2 is 16. So these are all of the extreme values that I would have to check. It tells me, looking at this value is the smallest, and this one is the largest on that interval. I would also be able to tell you that this one is not Extrema because when we're looking at its picture, it doesn't fit the description. It is not a largest or smallest value. It is flat there. Stuff is above and below it. There's no way to make that extreme as a value. All right. So same rules apply. Try doing it with this next function here, 2x minus 3x to the 2/3. I'm going to give you a couple minutes to walk through this on your own. Remember, you're looking for critical points. That is where it is equal to 0 and undefined. That helps you find where it could be, say, a peak or a valley. And you're also looking for the endpoints, right, which may not be included in the critical numbers. Okay, so let's see if you're getting the hang of it. First thing you need here is a derivative. So the derivative is going to be 2 minus 2x, and this will be to the -1/3. And I have to see if there's a place where this is equal to 0. I'm actually going to write it like this. And so critical numbers happen where it's undefined and where it's equal to 0. So let's see if we can find this. Is there a spot where this happens? Now it is possible to solve this equation, and I'll do that for you, but there's also some common sense involved here. Maybe some of you can see that answer quickly. But now that I've moved it from one side to the other, I can cross multiply. So I'll have 2 over 2 is x to the 1/3. So 1 is the cube root. And the way you get it out of a cube root, any ideas? Yeah, you cube it, but you have to do the same thing to both sides. So this would be the process if we were working on that kind of exponential equation. So 1 is the value of x. The common sense part of it that I was trying to hint at is the only way 2 minus something to equal 0, it has to be 2. 2 minus 2 is 0. So you'd have to make this bottom equals 1 in order to get it equal to 0. But anyways, either way, we end up here with x equals 1. All right, so critical point, x equals 1. Anywhere else? Yeah, we definitely need to check out start and the finish. Thank you for reminding me. But is there anywhere else where we might have a critical number? Good. X equals 0 is a critical number. How come? It's undefined there. If x equals 0 here, I'm dividing by 0. So I also have to include x equals 0 in my list. So here's my candidates. These are the endpoints. And here are my critical numbers. Somewhere within this short list is the minimum and maximum value from -1 to 3. Now again, that just shortened the list down. Now we can search a much smaller group than having to look at every possible, guess that you could make on that interval. So I've already plugged it into my calculator to help get us going, and I'm going to just use the table to show you. So again, make sure that when you set up your table, so that second function window, it should be on ask here for the independent. That way you get to put in the values. And the table is this one right here. You go second function, and you do that. Now, this is not necessary. It just makes life easier, because now all I need to do is say, use -1 for x, use 3 for x, use 1 for x, and use 0 for x. So here are the choices that I have, and I'll just transfer them onto my sheet now. So according to that theorem we just talked about, now I can tell you what the smallest value and the largest value are on that interval. This, without even looking at the graph, must be the minimum, and this must be the maximum. Okay. So let's go and verify that with the picture. So you can see the corner here. That's the corner that we found. It didn't turn out that the corner was, it does turn out that the corner is the largest value at 0. And -1, which is here, that's the smallest value. Everybody else is sort of underneath that, between those two. What else could we say when we look at this? Well, these are my endpoints. So the only reason I'm including them is to check to see the biggest and smallest values there. The value here at 1, is that extrema? There's 1 right there. Do you think that's an extreme point? Really? No? Maybe I'll zoom in so we can see it better. It doesn't need to be as tall as that one is. Let's go from -5 to 0, just like my work says. So you'll see the corner better this time. And there's the value at 1. You can see the curve happening better as well. So I'll ask again, which means you probably know what the answer is. But do you think that x equals 1 is relative minimum or not? It is, in fact, a relative minimum. The criteria is that it is the minimum for some interval on that graph. So it's not the minimum, way out here. These values are clearly smaller. But if I was just to go from there to there, that's one interval where it's the smallest value. That's all you need to make yourself a minimum, is one interval where it's the smallest. So you can make your interval as small as you want in order to make that work, right? I could go from, where the mouse is here to here, and that will still be the smallest. But it's a little easier to tell if I move it a little farther out, like from here to there. That's still the bottom of that piece of the graph. You only need 1 to say that you're a relative minimum. Okay, so find the relative extrema. This time we're doing the same process with a trig function. So just, I know it's always one of those things. I'm giving you a little hint here to make sure that the math doesn't trick you up. But just see if you can get through this process of finding the extrema on 0 to 2 pi. Okay, so a little trip down memory lane there for grade 12 solving trig equations. Can somebody confirm that at least I'm on the right track here? I end up with cos x equals 0, which happens at pi over 2 and 3 pi over 2. That's the x coordinate on the unit circle, so where x equals 0. Then I get 1 plus 2 sine x equals 0, so sine x equals negative a half. That means because sine is negative in quadrants 3 and 4, that's where I'll find my answers. And the reference angle I get is pi over 6. So I think I'm okay here. That means I have 4 places to check as well as my endpoints. So these are the candidates we're going to be looking at. Which again is nice if you have the table set up to use in your graphing calculator. Certainly saves you a lot of button pushing. So let's get that equation in. So the original one is what I'm going to be looking at. I only use the derivative, remember, to give me the information about that original. So I have 2 sine x minus cos 2x. Oops, and I forgot a bracket in there. And at this point, I'm not going to look at the graph. I'm just going to use the table method. Again, I need to check that I'm in radians, so that's good. And this time, I'm interested at 0. I'm interested at 2 pi. I'm interested at pi over 2. 3 pi over 2. And 7 pi over 6. And then finally at 11 pi over 6. Oops, did I put that in right? I might have made a mistake there. 7 pi over 6. Okay, and then 11 pi over 6. Okay, so according to the work that I've got here, I'll transfer this to my page. I get -1, -1, 3, -1, -1.5, and -1.5. So from the information I've been working on, that right there is the maximum. And these two here either could be the minimum. So if you're trying to think about, that's just, it's nice when you have 2 choices. This is like maybe your employees only have to work 4-hour days or 12-hour days. If you want to be mean, then you can make them work 12, and if you want to be nice, you can make them work 4. Well, but anyways, if you have more than one choice at minimizing whatever you're doing, then you obviously can strategize about which one you wanted. But then these ones, remember, were my endpoints, so I don't expect anything special about them. But I should be able to now tell you, what about the other values? Let's take a look at the graph and see which ones actually fit the description. And I should just pause this for a second here, because of course my window should go from 0 to 2 pi. And I know that it goes from -1.5. That's the smallest, so I guess I'll make this -2. And the largest it gets is 3. So there's a picture of the graph. There's the double minimum right there, and there's the maximum right there. So what do we think here? 3 pi over 2, that's going to be, let's see here, 0, then 3 pi over 2, so it's going to be right around double minimum. So it's going to be this one, I believe. So does that fit the description? Is that a relative minimum or maximum? Yeah, basically you're looking for a little hill or a little valley. As long as you can make one hill or valley where it's the biggest or smallest, that's going to be extrema. So in this case, yes, that one is a relative minimum as well. As are the other ones. There's the bump at 7 pi over 6, and there's a bump at 11 pi over 6. Those are the minimums. And there's the bump at pi over 2, which is the maximum. Okay, so this is this unit that we're working on. We're taking the skills that you have, and we're trying to show you some places where that gets applied. If you're happy with life so far, then you can just kind of follow me as I do this. This is optimizing an optimization problem. I'm just going to be showing you where this can actually be used as well. So, you know, if you're really with it and you want to go ahead, you can work it out with me. Otherwise, if you're happy to just watch, that's fine too. Okay, I just don't want anyone to feel like this is you know, that this is the reality now. Okay. So here's an example problem that somebody would most likely use a computer to work out, but that computer would be doing exactly what we're doing here, which is to say, if you're going to drill from an oil rig to a refinery, you need to build a pipeline. So if your pipeline is in the ocean, then you got to lay pipeline down, and that's quite expensive to go deep underwater and to hire the crews to do that. It's quite a daunting engineering feat as well. Compared to doing it on land. So you would expect that it's more expensive to put that pipeline down in the water than it is to do it on land. So here's the costs that we've been given. $500,000 for every mile that you do on land, on the water. And for every one that you do along the land is $300,000. And what we want to do is minimize the cost, because we don't really care how long the pipeline is. It just has to pump the oil from the rig to the refinery. What we do care about is the cheapest pipeline that we could build. So here's, for example, some possible attempts that we could do. The rig is 12 miles offshore, and it's 20 miles down from the refinery. So we could just go the shortest possible underwater road and then the longest possible above ground, because that would minimize the amount of underwater pipeline, right? The other thing you could do is you could just say, well, let's maximize the underwater pipeline, use all of it to get to the refinery. Why would that make some sense? Some of you might be like, that's dumb. Why would you want to do the most expensive road? It might actually turn out to be the best one. Why? It's the shortest distance, right? A direct line from the refinery to the rig. So that may end up making some sense as well. We also may want to do some combination. For example, part of it being in the water, and then the other part of it being along the land. So let's work out what these things could be. First, what I'm going to need to do is come up with a function that models the cost. Okay, so the cost of this pipeline, so I'll call it C of x. And we only want to do one variable, which is why it's nice that the picture here is showing you how to get one variable out of this. If I use x as the distance along that the ocean, I should be able to figure out all of this with one variable, because this distance, which is 20, I can connect them all. So I'll show you how you do that. I know this distance and I know this distance. That's Pythagorean Theorem that gets me the rest of the way. So this one here is x squared minus 12 squared, which is 144, and the square root. That's how long this piece is right here. Okay. So if I use that up, and let's just say I plug those numbers in my calculator and it says, oh, that's 5 miles. How far do I have to go along the land? So this horrible mess here, yeah, if we said hypothetically it was 5, then 20 is the whole thing, there'd be 15 left over there. So the way you come up with the function is, this is the 20 miles, take away whatever you had over here. So x squared minus 144. So here's my cost function then. X is the amount of pipeline under the water, which is 500,000. So I'll just use 5 to represent hundreds of thousands. 5x plus 3, as in the 300,000 per mile along the land, times 20 minus x squared minus 144. Okay. So this is going to be, let me just expand this. It'll be easier for us to take a derivative. Okay. And now all we're going to do is find a derivative, and then we'll employ the calculator to do some of this work for us. It is possible to solve this one nicely, but I'm not going to drag you through the mud your first day back anyways. But let's take a derivative here. This cost function has a derivative of 5 minus, so this might be a good practice review of chain rule for you. There we go, I hope. And those 2's there, I'll remove out. So I have 5 minus 3x over root x squared minus 144. So there's a couple critical points that I'm going to go looking for, the critical numbers. Can anybody see one right off the bat? Yeah, good. 12 is one that would be of interest to us because 12 would cause a division by 0 here. That's one of the extreme values, and that corresponds to this situation right here. If x equals 12, that's what I just did, right? There's another one that I'm going to be looking at, which is when these two pieces are equal to 0. And again, if we go ahead and solve this, it does work out nicely, but let's go and use the calculator to do it. So I'm going to put that in as my function here. It is 5 minus 3x over the square root of x squared minus 144. And yeah, I think we were good there. Now, when you think about the window here, the largest value that you could possibly do for x is going to be this diagonal length all the way straight to the refinery here. So if you wanted to know like what would be a good guess, maybe start at like 50, but that'll probably give us more of a window than we need. And I only need to see where it's equal to 0 because that's the critical numbers I'm looking for here. And there it is. That's the point I'm interested in right there. So maybe I'll zoom in on that just to make the calculation a bit easier to deal with. So let's zoom in. Okay. And I'll calculate a 0. So where the cursor is right now, if I'm just trying to get an idea, it's about 15 is my answer. So when I calculate a 0 with the TI-83, a good left bound, would be something like 14, and a right bound, 16, and then I'll guess that it's 15, like I said with the cursor. And there, it comes back. So the derivative is equal to 0 when x is 15 miles through the water. Okay, and as I mentioned, the other scenario that you want to check here is this one. So let's go find it in our calculator to see. What if we took the shortest road, even though it's the most expensive? Okay. So that would be 23.32 something, which is this one straight along the water. Okay. So I know what my original function is. It's this one right here. That's what I'm going to now use with the table just like we did before and see what we have. So don't want to see the derivative anymore. We're going to put back in, this is the cost. And find out where the minimum cost is, because I'm sure our boss would prefer that we do the cheapest rather than the most expensive one. Okay, and now I have the cost. I'll plug them in here. So those aren't even in the domain, which is why I'm getting, let's just get rid of that. Okay, anyways, all we're interested in 12, and we were interested in 15, and we were interested in, the calculator is pretty handy at storing the answers. So the one that I just did, which was that 23 point, etc., that's the other one I'm going to check here. So here are my scenarios. This is the one when I get out of the water as quickly as possible. That's this scenario right here. And it turns out to be the most expensive. It's actually, I believe, $12 million according to ours. The next scenario we found was when we minimized the cost function, and we found that it's equal to 15 when it equals 0. And that's actually going to be the cheapest. So 15 is this one here, when we go part way along, a little more than 12, but less than the 23 that would be the whole way. And that's going to be 10.8 million. So already you've just saved $1.2 million in that 5 minutes of your life. So it's a pretty good salary, I guess. And then if you were to have just gone straight through the water, that's $11.6 million, which is still better than getting out of the water as fast as possible. But the good thing about knowing this strategy is you can confidently say there is no other possibility to minimize your cost. This is it. If it's not one of these three, you're wasting your time trying to figure out a different way to lay this pipeline down. So you know without any doubt the cheapest one is to do here with 15 miles along the water. So 15 miles underwater, and then it would be 12 squared minus, 15 squared and this is how far we'd be going along the shore. So 20 minus 9 is 11. That minimizes your cost. All right, so again for today, I'm happy if you understand how it works on just the regular graphs and functions, but eventually we're going to be thinking about these optimization problems as far as finding minimums and maximums in real life.